How differently do different balls fall? The simple but remarkable answer to that question is that all balls fall at the same rate. Now, remember, we're neglecting air resistance, which is a pretty good approximation for balls that you just drop in front of you. But don't try to apply the same story to a sheet of paper, because the sheet of paper is really affected a lot by air resistance. So returning then to the balls and this question, whether it's a basketball, a tennis ball, a handball, a golf ball, or a baseball, if you drop them together, they all fall together. So here we have a tennis ball and a basketball. We'll see whether they fall together. Ready? Get set, go! Exactly together. Exactly together. Not only do all balls fall together, but if you were to begin falling with them, you'd keep pace perfectly. You'd all fall together. Well, we can do that. Now, I'm not going to take you and drop you with a bunch of balls, but I can allow you to take that trip with this gadget. So here I've got a frame with a camera mounted on it, and Catherine and I are going to let this frame fall down a pair of strings. So it'll plummet down to the ground in a somewhat controlled way with springs at the bottom so that it comes to a safe stop near the ground. And you'll be looking out that little window at the world in front of you and the balls that are dropping as you drop with them. There's you guys. There's Catherine down there. Hi down there, Catherine.
Hi.
You ready to have some balls and a camera drop at you?
We're ready.
All right. All right, everyone. Here you guys go. Ready, get set. Ready, get set. Ready, get set. Ready, set, go. 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 3, 2, 1. You're probably wondering whether one of those falling balls ever hit the camera down below where Catherine was standing. The answer is yes, and it wasn't pretty. That's one of the reasons why I didn't drop a bowling ball. Why does that happen? Why does a bowling ball and a baseball fall together and hit the ground at the same time? After all, the bowling ball weighs much more than the baseball. So from a weight point of view, the bowling ball is pulled downward much more strongly by the Earth's gravity than the baseball. And so the bowling ball should accelerate faster. It should clearly outpace the baseball and hit the ground first. What's wrong with that thinking? Well, there's another difference between the bowling ball and the baseball, apart from their difference in weight. The bowling ball has much more mass than the baseball, which is to say that it's an awful lot harder to shake a bowling ball and to make it accelerate first away from me, toward me, away from me, toward me, much harder than just shaking a baseball, right? This guy accelerates very easily in response to small forces. So, from the point of view of mass, the baseball is the more responsive one. Less mass, so when it's pulled downward by the Earth's gravity, it should accelerate faster. It should clearly outpace the bowling ball, and the baseball should hit the ground first. We've got two opposite predictions. From the weight point of view, the bowling ball should hit first. From the mass point of view, the baseball should hit first. And actually, from observation, we know that both of those predictions are just wrong. The two balls hit together. So, what have we done wrong? Well, you can't separate the weight point of view and the mass point of view. You have to combine them. We have to have one point of view in which we take into account both the higher weight of the bowling ball and the greater mass of the bowling ball. And when we put those all together and do the analysis more carefully, we discover that, yeah, the bowling ball has more weight. It's pulled downward harder, and that alone would make it go accelerate faster. But it also has more mass, so it resists accelerations more, and that alone would slow its acceleration. The two together, more downward force, more mass resisting that force, those two increases cancel perfectly. So the bowling ball's response, that is, its downward acceleration caused by gravity, the Earth's gravity, is exactly the same as the downward response of the baseball to the Earth's gravity. The two balls accelerate downward at exactly the same pace and hit the ground together. When you're carrying a ball at constant velocity, the ball's moving at constant velocity, you're most aware of the ball's weight because you're having to support that weight. Without your upward push on the ball would fall. And so you have to push up just enough to balance the ball's weight. And you know it. You feel that you're pushing up. So you're detecting gravity as you walk along at constant velocity. When you push a ball back and forth on the table, you're causing the ball to accelerate, first one direction and the other. You're changing its velocity. And as a result, you're quite aware of the ball's mass, its resistance to acceleration, or the measure of its inertia. The table, on the other hand, is supporting the weight of the ball. So you're completely oblivious to that weight. It could be large, it could be small. That's the table's responsibility. Yours is the acceleration and therefore the mass of the ball. Now, this course is about the objects of everyday experience and the physics concepts that make them do what they do. In other words, it's about understanding how things work more than it is about calculating how they work. That said, however, there are times when looking at the quantitative physics, opening up the hood, and staring at the mathematics that underlie the concepts is a useful activity and will give us insight into how the machinery of our universe works. This is one of those times. So bear with me as I do a little bit of algebra to look at why all balls, when dropped from rest, fall together. When a ball is falling, the only force acting on it is its weight. So the net force on a falling ball is the ball's weight. Well, Newton's second law of motion tells us that the acceleration of any object is equal to the net force on that object divided by the object's mass. So in this specific case of a falling ball, the acceleration of a falling ball is equal to the net force on the ball, which is the ball's weight. So it's the ball's weight divided by the ball's mass. That's pretty simple. The falling ball's acceleration is equal to the ball's weight divided by the ball's mass. But we can make it simpler. We can make it simpler because we know something about the ball's weight. Here, near the surface of the Earth, a ball weighs 9.8 newtons for every kilogram of mass it has. That is, its weight is proportional to its mass. And the constant of proportionality is 9.8 newtons per kilogram. For those of you who prefer to talk about pounds, because newtons is kind of a esoteric concept, that's about 2.2 pounds force per kilogram of mass. All right, so we now know something about the weight. We can substitute in this version of the weight, that is, that constant of proportionality times the mass of the ball. When we do that, we discover that Newton's second law becomes quite simple. It's the acceleration of a falling ball is equal to that constant of proportionality times mass divided by mass, the ball's mass divided by the ball's mass. That cancels. The ball's mass disappears from this Newton's second law, and Newton's second law says that the falling ball's acceleration is simply the constant of proportionality, which is to say, a falling ball's acceleration is 9.8 newtons per kilogram, or equivalently 2.2 pounds per kilogram. Done. Well, that's a strange result. It's kind of cool. What it says is the ball's mass doesn't matter. The acceleration of this ball is the same as the acceleration of this ball. The mass was unimportant, and this is consistent with our observation. You drop all these balls, they all go down together. They all accelerate downward together. But what remains to be done, and it's bizarre, is that constant of proportionality has wacky units. 9.8 newtons, that is a unit of force, per kilogram, that is unit of mass. That doesn't sound like an acceleration. Recall that the SI unit of acceleration is the meter per second squared. So where is the connection? Well, it turns out that the unit, this unit's Newton per kilogram, is exactly the same as this unit, the meter per second squared. They're the same. And how does that ever happen? Well, it turns out that the Newton is defined in an interesting way by Newton's second law. 1 Newton is the force that causes a 1 kilogram mass to accelerate at 1 meter per second squared. That defines the Newton. And as a result, Newton's second law, written out in that way, says that 1 meter per second squared of acceleration is equal to 1 Newton of force divided by 1 kilogram of mass. Get rid of the ones, and you have the meter per second squared is equal to the Newton per kilogram. They're the same unit. As a result, that little g constant of proportionality is an acceleration. It is 9.8 meters per second squared, and that is the acceleration of any falling object here near the Earth's surface, as long as air resistance can be neglected.